Imagine traveling across galaxies, seemingly faster than light. It sounds impossible, right? And according to Einstein, it is. Nothing with mass can move through space faster than light. No rocket, no spaceship, no engine. Nothing. But here's the strange part. What if we don't move faster through space, but try moving space itself? That sounds like cheating, and honestly, it kind of is. This idea is called a warp drive, and by the end of this video, you'll understand why it's one of the coolest ideas in physics. First, why do we even need something like this? Because space is not just big. Space is so large that it breaks human intuition. The closest star to Earth, besides the Sun, is called Proxima Centauri. Proxima literally means near. Sounds comforting, except it is about 40 trillion kilometers away. And that number is so huge, it basically means nothing to the human brain. So let's make it easier. The fastest object humans have ever built is a space probe. At its top speed, it travels around 700,000 kilometers per hour. That is insanely fast. That is New York to Tokyo in less than a minute. Now aim that thing at our nearest neighboring star. How long would it take? About 6,000 years. If ancient Egyptians had launched it while building the pyramids, it would still be flying today. And that is just the closest star. Our galaxy has hundreds of billions more. So rockets are not going to solve this. Not because rockets are too expensive, not because we need a bit more technology, but because the distances are simply ridiculous. So scientists started asking a different question. Not, how do we build a faster rocket, but is there a completely different way to travel? To understand the trick, we first need to understand the rule. Einstein's speed limit. Light moves at about 300,000 kilometers per second. That is the fastest speed anything can travel through space. But why? Why can't we just build a bigger engine, add more fuel, and keep accelerating? Here's the simple version. The faster something moves, the more energy it takes to make it go even faster. At normal speeds, that is not a big deal. But as you get closer and closer to light speed, the energy needed starts to explode. Going from 90% of light speed to 99%? Insanely difficult. Going from 99% to 99.9%? Even worse. To actually reach the speed of light, you would need infinite energy. Not a lot of energy. Not all the fuel on Earth. Infinite, which means impossible. This is not like a highway speed limit where you can break the rule and risk a fine. This limit is built into the structure of the universe. Every experiment we have ever done agrees with it. So is that it? Game over? Are the stars locked away forever? Maybe, but maybe not. Because Einstein's rule has very specific wording. Nothing can move faster than light, through space. But it does not say space itself has to behave like a fixed, solid stage. And this is where things get weird. Einstein also showed us that space is not just empty nothing. Space is a physical thing. It can bend. It can stretch. It can squeeze. A common way to picture it is like a giant rubber sheet. Put something heavy on it, like a planet, a star, or a black hole, and the sheet curves. That curvature is what we experience as gravity. Earth orbits the sun, not because the sun is pulling it with an invisible rope, but because the sun bends space-time, and Earth follows that curve. So space is flexible, and we already know space can stretch. In fact, the universe is expanding right now. Far away, galaxies are moving away from us because the space between galaxies is growing. Some are so far away that the distance between us and them increases faster than light could cross it. Is that breaking Einstein's rule? No, because those galaxies are not flying through space faster than light. The space between us is expanding. That is a huge difference. So space can stretch, space can bend, space can change. And the normal speed limit does not apply to space in the same way it applies to objects moving through space. In 1994, a physicist named Miguel Alcubierre asked a wild question. Could we use this loophole on purpose? And yes, He was partly inspired by Star Trek. But he did not just say, "Wouldn't warp drive be cool?" He did the math using Einstein's own equations, and the result became known as the Alcubierre drive. Here's the idea. Your spaceship sits inside a bubble of spacetime, a warp bubble. Inside the bubble, the ship is not racing forward. It is not breaking the speed of light. It is basically standing still. But the bubble itself does something extreme. It squeezes space in front of the ship and stretches space behind it. So instead of the ship moving through space, space moves around the ship. Still confusing? Imagine you are standing on a carpet. Think of the carpet as space itself. A point far away on the carpet would normally take many steps to reach. But now, the carpet in front of you gets squeezed together, so that faraway point becomes closer. At the same time, the carpet behind you stretches out, helping push your small patch of carpet forward. You are not walking across the carpet. Your patch of carpet is being carried by the carpet itself. You never take a step, but the room seems to slide past you. That is the basic idea of a warp drive. Compress the space in front, expand the space behind. And here is the genius part. Inside the bubble, the spaceship is not moving faster than light through space. So Einstein's speed limit is not technically broken. The ship stays inside its own local region of space. The bubble does the traveling, and mathematically, this is not just fantasy. The Alcubierre warp drive is a real solution to Einstein's equations of general relativity. On paper, it works. So, why are we not already packing for Alpha Centauri? Because the math comes with a very serious problem. To bend space in this exact way, you need something extremely strange. You need negative energy. But what is negative energy? Everything familiar to us, rocks, air, water, people, planets, stars, has positive energy. Positive energy creates normal gravity. It pulls things together. Negative energy would do the opposite. It would push space apart, almost like anti-gravity. Physicists often call this kind of requirement exotic matter. And the problem is simple. We have never found exotic matter in the amount we would need. Not in space, not in a lab, not anywhere. There is a tiny technical exception. In quantum physics, the world of the extremely small, effects that resemble negative energy can appear briefly under very special conditions. But the amounts are absurdly tiny. Imagine needing enough material to build an entire city and having only a single grain of sand. That is roughly the problem. And it gets worse. The first calculations for a warp bubble required more energy than exists in the entire observable universe, which is not exactly practical. Later versions improved the math a lot. That sounds encouraging, but a lot better still does not mean easy. Some estimates still require something like the energy of an entire planet converted perfectly into pure energy. And even if we somehow had that energy, we would face more problems. How do you create the bubble? How do you steer it? How do you send signals to the front of a bubble if information cannot travel faster than light inside it? How do you turn it off? And some calculations suggest that particles and radiation could build up at the front of the bubble during the trip. Then, when the bubble stops, that energy might blast forward toward your destination, which is a pretty terrible way to say hello to another star system. So let's be very clear. A warp drive is a real idea in theoretical physics, but it is not a machine. Nobody has built one. Nobody knows how to build one. Nobody has shown that faster than light warp travel is physically possible. And it is completely possible that the universe simply does not allow it. But here is why the idea refuses to die. Because the math is not nonsense. It came from Einstein's own theory. And real physicists still study versions of it today. Some models try to reduce the energy requirement. Some explore different bubble shapes. Some look at warp-like effects that might not need exotic matter, although those versions do not allow faster than light travel. All of this is early. All of it is theoretical. A lot of it is debated. So let's separate science from science fiction. Right now, there is no evidence that a faster than light warp drive is possible. But science doesn't stop there. Because we also haven't proven that every version of the idea is impossible. And that small gap between we cannot do this and this can never be done is exactly where science lives. That's what makes the warp drive so fascinating. It's not just a concept for interstellar travel. It's a question about reality itself. Maybe faster than light travel is forever impossible. Or maybe, someday, someone finds the missing piece. History is full of ideas that once seemed impossible. Flight, space travel, the moon landing, all once out of reach until they weren't. And it always began the same way, with someone asking, what if? And if you enjoyed this video, hit subscribe so you don't miss the next one. Until then, see you.